Vibration case study 3.3 is a bit about biodynamics induced loading. This is the Millennium Bridge in London. London has some very interesting rules where if you're standing in a certain place, you are legally protected to see certain landmarks, right? And so they have these rights of view, and you can't build anything that would get in that right of view. That's why the Shard in London has this really weird shape. It's to get out of the way of the rights of view. They wanted to build a bridge across the River Thames, and if they had built a normal pillar, one of the pillars would have been in the rights of view, right? So they had to spread the pillars out into this Y shape. And bridge designers are fascinating people, and sometimes they can be very egocentric. And this gentleman made this bridge, and it was supposedly the most beautiful bridge in the world, right? The problem was, and you can go out and find videos from when it opened in 2000, about 2,000 pedestrians, so about 1.5 people per square meter used the bridge. And it started to shake laterally, left and right, with all the people, right? What happens if something starts to shake? You start to try to go with it. So now you have 2,000 people on a bridge actively trying to shake the bridge left to right. And it's a positive feedback, which is not what you want in an engineering system, right? You always want negative feedback. And so you get this system, and they had up to about 1/4 of a G of acceleration. So this whole thing was on the verge of coming down. It took them a couple of years to add about 37 dampers. So you can see a damper here, and you can kind of see the base of a damper there and the base of another damper there. These dampers were put in by a company called Taylor Devices in New York. I actually have a patent that was bought by Taylor Devices, and then after a couple of years, they said, "Why do we own this?" And they let it go, which is fair. So it is expired now. You can use that for free. And what I love is that the whole bridge cost 18.2 million pounds in 2000, and it took them 5 million pounds to retrofit it with dampers. So almost 1/3 of the cost of the bridge just to get it, fixed back up. The team that designed this bridge went on to design the tallest bridge in Europe at the time in France. And it was under construction when London shut this one down. So that whole project also got stopped for several months while people were like, we don't trust your math, right? It didn't work so well up there. But it's interesting to think about how that design choice of moving them out farther, right, meant that you could get some biodynamic loading and resonance in a lateral direction. We've mainly been talking about things going up and down, but you could also get a degree of freedom in the lateral direction. And to solve that, because you're in resonance, the solution is to add more damping. And damping is the solution to pretty much all of your resonance.